So what we're trying to do is find the rate expression. Right.
And then we have to find the special units, right? Wait.
That's right.
Wait, I'm still stuck at solving for K.
That's right.
It makes sense for K to be 8.
You got 8 for K? That seems good. Okay, good. And you could use any row that you wanted in this case. So we should go back now and plug that in. Well, we know that K is 8. Maybe I won't plug it in yet, but that's 8. And now we do need to find those units. That's right. Well, let's work that out.
So would it be similar to last time that this would be like?
That's right.
And the K is the, wait, is that the liters over moles times seconds, or is it
What are we trying to figure out?
the units on K? Oh.
Right, so we can't plug in units for K. That's what we're trying to figure out. What we do need to do is plug in units for the rate.
Oh, it's on the table. Oh, I got it.
I haven't worked out an answer yet. Where's your work? You kind of maybe jump to the answer here.
Oh,
yeah. So yeah, it looks like there's a mistake. Maybe you didn't realize that these units have to be squared.
Yeah.
So we have to use the exponents that we've already figured out to get the right units. The concentration of H plus is in moles per liter, but the concentration of H plus squared is in moles squared per liter squared.
Okay.
Now what should we plug in for the units for the rate?
Well, that's still moles over liter seconds.
That's right. You could just look that up in the table. They told us that the rate was in moles over liters over seconds. But that's what any rate would always be in, so we don't need the table for that. We know that it's always in molarity per second.
Okay.
And molarity per second is always... One thing that's important here is I'm not going to plug even plug in the number 8 for K. Because I don't care about numbers here, I care about units. So plugging in the number 8 for K is just going to confuse me at this point. But I have to leave K in the equation, so I can solve for the units for K. So this is the best way to set up this equation. I plug in the units for everything besides K, and now we need to solve for K. you got for the units?
Yes. Yep.
8 liters cubed, moles to the -3, seconds to the -1. So this would be a good answer for the full rate expression. Suppose I wanted to find the rate if all the concentrations were 0.3. How would I do that?
Just plug that in the.
Plug it in.
Yeah. I have to remember that this would be 0.3 squared when I plug it in. Okay, well, we don't need to work that out, but we could use the rate expression then to figure out what the rate would be in that case. So what is the order of this reaction?
Oh, 4.
That's right, you add the exponents. If you add the exponents, that gives you the order of the reaction. Now we would call this the overall order. Now you could also say that it's first order in BrO3 minus, and it's first order in Br minus, and it's second order in H plus, and the overall order is 4. So you can talk about the order for a particular reactant, or you can talk about the overall order. If they just say order, they mean this. They'd have to specify if they wanted the order for a particular starting material.
I have a question. Does this have anything to do with what we did today with the graphs and you decide if it's first?
That's something hopefully we'll get to in a second. No, it's a different topic.
Okay.
Yeah.
Just checking.
That's a different topic. That's it. So there's actually 2 different types of rate expressions that you've covered in this chapter, and we're just about to finish with this type and move to the other type. Okay. So let's make sure that we're done with this. So we talked about the orders. By the way, what is 5 to the 0th power?
1.
Good. What's 7 to the 0th power?
1.
Good. So suppose that you got, say, 2. No, let's suppose that you got 1 equals 3 to the x. What would x be?
0.
Yeah. That didn't come up in any of the examples that we looked at, but that's possible that that could come up. That would be if the reaction was 0th order in something. That's a little bit unusual because that means that if something had an exponent of 0, that would mean that it just was 1 and its concentration didn't matter for the rate. If you're 0th order in a particular reagent, that means that that reagent just doesn't matter for the rate. For example, if this was a 0, then this would always be 1. And it wouldn't matter what the BrO3 minus concentration was. So if you're 0th order in a particular substance, that means that that substance doesn't matter for the rate. That's kind of unusual, but that can sometimes happen. They give an example in the book of how sometimes when you're using a catalyst, you can be 0th order in something. All right, so that's something that you could possibly discover from this rate data, that you were 0th order in something. What that really means is that you can drop that term out of the rate expression, because this would just be 1, right, if it has an exponent of 0. Of course, that's not what we had in this case. Now, the other type of rate expression you guys are covering, notice that this is a rate expression that says, by the way, suppose I doubled this concentration. What would happen to the rate?
It would double.
Yeah. Suppose I tripled this concentration. What would happen to the rate?
Triple.
Suppose I doubled this concentration. What would happen to the rate?
Quadruple.
Yeah, because 2 squared is 4. And suppose I tripled this concentration. What would happen to the rate?
To the 9.
Yeah, the rate would be multiplied by 9. So that's one way that we can use these exponents. That means that this concentration affects the rate more than this concentration. The bigger the exponent, the more you affect the rate. We were just saying that if the exponent is 0, then that concentration doesn't affect the rate at all. Okay, now this type of rate expression that we've been looking at, this is called the rate law. It's also called the differential rate law. Did your instructor ever use that term? Okay, differential rate law. When people say rate law by itself, what they mean is this differential rate law. This shows how the concentrations affect the rate. By the way, if we increase the concentrations, would we usually expect that to increase or decrease the rate? Yeah, usually if you have more starting materials, you would expect to have a greater rate. There's another type of rate expression that tells you how the rate changes over time. So those are the two different types of rate expressions. There's one rate expression that depends on concentrations, and now we're going to talk about the rate expressions that depend on time.